All right, let's talk about big data. It's one of those buzzwords that's everywhere, right? But what is it really? Is it just a ton of data? Well, sort of, but that's not the whole story. Today, we're going to peel back the layers and go from that buzzy, vague idea to a solid blueprint of what makes it tick. So let's get into it. So here's our game plan. We'll start with why you should even care about this stuff. Then we'll get into the famous Bs that really define the challenge. After that, we'll see how we can possibly manage this flood of data, lay out the architectural blueprint, and finally, look at the cool tools that make it all happen. Just to set the stage, get a load of this number. 175 zettabytes. That's how much data we're expected to create as a planet every single year by 2025. You know, a zettabyte is a trillion gigabytes. It's a number so big it's almost meaningless. It just tells you that the old way of doing things, it's completely broken. Which brings up the real question, doesn't it? Is big data just about being big? Not even close. The real problem, the thing that forces us to rethink everything, isn't just the size. It's a few other troublemakers that come along for the ride. And that brings us to the famous Vs of big data. You can think of these as the defining features of the problem we're trying to solve. You might hear people talk about 3 or 5 or even more, but we're going to cover the essentials. So first up, the obvious one, volume. This is the sheer scale of it all. We're not talking about spreadsheets anymore. We're talking about so much data that no single computer on Earth could handle it. You have to spread it out across a whole army of machines just to store it. Next, we've got velocity. This is all about speed. Think about a social media feed or sensor data from a smart factory. It's not a trickle, it's a fire hose. And you often need to analyze that data the very instant it arrives, which is a whole different ballgame. Then there's variety. You know, something like 80% of all data out there is what we call unstructured. It's messy. It's emails, photos, videos, audio files. It's not the neat and tidy stuff that fits perfectly into a traditional database. It's just stuff. And we have to make sense of it all. Veracity is a huge one. It's about trust. How reliable is your data? It's often messy, inconsistent, and full of gaps. Is John Smith at this address the same person as Jay Smith with a different zip code? Figuring that out at scale is, well, it's a massive headache. And finally, we get to the most important V of all, value. Because let's be real, who cares about all the volume and velocity if you can't get something useful out of it? The entire point of wrestling with this monster is to find insights that help you make better decisions. Without value, it's all just digital garbage. So with all those challenges, how on earth do you tame this beast? You can't just build a bigger computer. It's not possible. The only answer, the fundamental principle behind all of big data, is to distribute the work. And that leads to two different ways of thinking. Scaling up is the old way. You just buy a bigger, badder, more expensive mainframe, a supercomputer, but you eventually hit a wall. Scaling out is the new way. You take hundreds or even thousands of cheap, regular computers and link them together to work as a team. That's the only way big data works. And you know what's wild? This isn't some grand new idea. The brilliant computer scientist Grace Hopper said this decades ago. She saw it coming. The entire big data world is basically built on her vision. Okay, but spreading everything out over a network isn't magic. It comes with its own set of rules and, more importantly, its own compromises. And the biggest rule in this world is something called the CAP Theorem. It's a fundamental law of the land for any distributed system. So here's the deal. They call it the pick two rule. You have 3 things you want. Consistency, meaning everyone sees the same up-to-the-millisecond data. Availability, meaning the system always responds. And partition tolerance, meaning it doesn't fall over if some machines lose connection with each other. Here's the kicker. Network failures always happen. So you have to pick partition tolerance, which means you're forced into a choice. Do you want to be perfectly consistent or do you want to be perfectly available? You can't have both. Every big data system has to make that trade-off. Okay, so keeping those trade-offs in mind, how do we actually put one of these systems together? Let's sketch out the blueprint for how you get from a mountain of raw data to an actual useful insight. It pretty much always follows this path. You've got your data sources. Then you need to ingest that data, either in big chunks, that's batch, or as a constant flow, that's streaming. Next, you have to store it somewhere. Then you process it, which is where the magic happens. And finally, people consume the results on dashboards or reports. Now, there are 2 major philosophies for building this pipeline. The Lambda architecture is the belt and suspenders approach. It has a slow, super accurate batch layer for historical data and a separate fast speed layer for real-time stuff. The Kappa architecture looks at that and says, that's too complicated. It just treats everything as a fast-moving stream, which can really simplify things. So that's the blueprint, the how. Now let's talk about the what, the actual tools you'd find in the big data toolbox to build these systems. When it comes to storage, we often reach for something called a non-SQL database. Non-SQL just means not only SQL. It's not one thing, but a whole family of databases, like key value stores or graph databases, that are built from the ground up to scale out and handle all that messy variety we talked about. The bedrock for many, many big data systems is HDFS, the Hadoop Distributed File System. Think of it as a giant virtual hard drive spread across thousands of cheap computers. It takes your enormous files, chops them into blocks, and scatters copies all over the place. So if one machine dies, your data is still safe. It's all about reliability at a massive scale. And for actually processing all that data, the original was MapReduce. It was a workhorse, super reliable, but kind of slow because it was always writing its results back to disk. Then Apache Spark came along and just changed the game completely. Spark does its work in memory, which is lightning fast. It's the difference between finding a book in a library versus having it open on your desk. That speed made it the undisputed king. Phew. Okay, we've gone through a lot of tech and theory there. But let's take a step back and tie it all together, because it's easy to get lost in the weeds and forget why we're doing any of this in the first place. So what are the main things to remember? First, big is about complexity, not just size. Second, the only way to handle it is to scale out with lots of machines, not scale up with one supermachine. Third, you need a good architecture to create a clear path from messy data to clean answers. And finally, and this is the big one, the only reason to do any of this is to find real, tangible value. And that really leads us to the most important question of all. For a long time, the challenge was technical. How do we analyze all this data? But we've gotten pretty good at that now. The new challenge is a human one. Now that we can analyze almost anything, what are the right questions to ask in the first place? That's what really matters. Thanks for digging into this with me.